A single gram of fuel could power a city for an entire year. This is the staggering promise of antimatter, the universe's most potent energy source and the key to reaching the stars within a human lifetime. By the end of this exploration, you will understand exactly why this dream engine remains locked in the realm of theory and what it would truly take to build it. We are going to dissect the physics of pure annihilation and confront the engineering nightmare of bottling lightning in a cage made of thought. How do you store a substance that vanishes in a flash of light upon contact with anything, even air? Can a structure be designed to withstand energies greater than the heart of a star? The answers lie at the bleeding edge of material science and quantum control. What does it say about us that we would even attempt to tame such a destructive force for the purpose of creation? That sugar cube of pure potential would not just fizzle or burn, it would vanish. In a single, silent instant, every atom of matter and its antimatter twin would cease to exist, their entire mass transforming directly into a flash of pure energy. This is not combustion, nor is it the complex splitting of an atom. This is annihilation, the most complete and efficient reaction allowed by the laws of physics. It is the direct application of Einstein's most famous equation, E equals mc squared, operating at 100% efficiency. Every single gram of mass is converted into energy. To understand the scale, consider a modern chemical rocket. To reach Mars, it must carry thousands of tons of liquid fuel, an enormous weight that itself requires more fuel to lift. An antimatter-powered ship, by contrast, might need only a few thousandths of a gram for the same journey. The difference is not incremental, it is revolutionary. 1 gram of antimatter, annihilating with 1 gram of normal matter, releases energy roughly equivalent to the bomb that fell on Hiroshima. Bottle that power, control its release, and you have the key to the solar system. The process itself is both simple and profoundly violent. When a positron, the antimatter counterpart of an electron, meets an electron, they both disappear. In their place, 2 incredibly high-energy gamma-ray photons are born, racing away at the speed of light. For larger particles, like antiprotons annihilating with protons, the result is a shower of even more exotic particles called pions. This is raw, fundamental power. Physicists like Dr. Gerald Jackson, who has worked on antimatter propulsion concepts for decades, call it the holy grail for a reason. The energy density is simply unmatched by anything else in the universe. So if the physics is so perfect and the energy so immense, why is our spacecraft still relying on controlled explosions of hydrogen and oxygen? The answer lies not in unlocking the energy, but in the terrifying challenge of holding it. That perfect fuel has a singular, absolute rule. It cannot touch anything. Not the walls of a tank, not a stray molecule of air, not even a speck of dust. The moment it does, the very reaction we want to harness happens immediately and catastrophically. The core dilemma of antimatter propulsion is not about creating the fire, but about designing a bottle that can never, ever break. That perfect bottle is a problem for a future we have not yet reached, because first, we must find something to put inside it. We must create the fuel itself, and this is where the dream of antimatter propulsion confronts a brutal reality of physics and economics. To obtain even a single atom of antimatter, you must build a machine of almost unimaginable scale and power. There is no antimatter mine, no cosmic reservoir we can tap. We have to make it from scratch, one particle at a time, in a process so inefficient it defies belief. The only tool for this job is a particle accelerator, a ring of supercooled magnets and vacuum chambers miles in circumference. Inside these tunnels, protons are whipped to over 99.999% the speed of light, and then slammed into a fixed target. In the debris of these microscopic collisions among trillions of other particles, a few antiprotons are born. It is like detonating an entire mountain of dynamite to find a single, perfectly formed grain of sand in the aftermath. The numbers are sobering. Researchers at facilities like CERN, which operates the sole source of slow antiprotons for research, have produced more antimatter than anywhere else on Earth. And yet, the total amount of human-made antimatter in history is less than 20 nanograms. To visualize that, 20 nanograms is about 1/1000th the mass of a single grain of rice. If you could somehow gather every antiparticle we have ever created and annihilate it all at once, the energy released would be enough to power a standard light bulb for just a few minutes. The scale of the challenge becomes clear when you consider the goal. To produce just 1 single gram of antimatter, a useful amount for a real spacecraft, you would need to scale up current production by a factor of billions. One estimate suggests it would take the entire output of CERN, running continuously, not for years or decades, but for billions of years. The energy required to run the accelerators would be millions of times greater than the energy the antimatter itself would ever release. From a pure energy accounting standpoint, it is the worst battery ever conceived. The cost mirrors this absurd inefficiency. While prices are theoretical, producing a gram of antimatter with today's methods could easily run into the trillions of dollars, making it by an immense margin the most expensive substance in existence. So why do we even try? The answer lies in a delicate dance of containment happening right now. Once an antiproton is created, its journey is not over. These particles are born moving at nearly the speed of light, and if they touch the walls of the accelerator, they vanish. To be of any use, they must be caught and slowed down. This is done in specialized devices like the Antiproton Decelerator, which uses magnetic and electric fields to gently herd these antiparticles, bleeding off their speed until they are slow enough to be trapped. They are then stored in magnetic bottles where they can be studied. But this leads us to the next, even more precarious step. Holding a few antiprotons for study in a lab is one thing. Storing grams of the material safely and for years aboard a spacecraft destined for Mars is an entirely different kind of nightmare. That cage of forces is our only answer to the storage conundrum. Since antimatter cannot touch a physical container, we must build a prison not of steel but of invisible fields. Picture a single, charged antiproton floating in the center of a perfect void. To hold it there, we use a device born from plasma physics called a penning-malmberg trap. It is a masterpiece of subtle control. A powerful, uniform magnetic field runs along the length of a cylindrical chamber, forcing the charged particle into a tight, spiraling path around it, preventing it from flying out sideways. Then, a carefully shaped electric field is applied to the ends of the cylinder, creating an energy hill so steep the particle cannot roll over it. The antiproton is caught, suspended in an invisible bowl of forces, unable to move in any direction without fighting its way uphill. This is the principle. The engineering, however, is where the dream meets a wall of staggering complexity. The chamber must be an ultra-high vacuum, a space emptier than the void between galaxies. A single stray air molecule drifting into the trap would mean instant annihilation. The magnets are not ordinary magnets. They are superconducting coils that must be chilled to near absolute zero with liquid helium, a process requiring immense and constant energy just to maintain the status quo. And the electric fields must be exquisitely stable. A single fluctuation or power hiccup could allow the precious cargo to drift into the wall. Researchers like those in CERN antihydrogen experiments have mastered this dance for small numbers of particles. They combine antiprotons and positrons to form complete anti-atoms, trapping them in these magnetic bottles to study their properties, their greatest triumph. Holding these anti-atoms for several minutes, This is the state of the art for containing the most powerful fuel in the universe. Now, consider the environment of a starship. The violent shudder of a rocket launch, the constant micro-vibrations of life support systems, the extreme temperature swings between sunlight and shadow in space. Could a device so delicate, requiring such perfect stillness and monumental energy input, ever survive that journey? The question exposes a fundamental tension. The very systems needed to contain antimatter are themselves fragile, power-hungry, and intolerant of any imperfection. A single micrometeoroid strike, a tiny electrical short, or a brief loss of cooling could collapse the magnetic bottle. The result would not be a slow leak, but a sudden, total conversion of the stored fuel into a devastating burst of gamma rays right inside the ship. This forces a sobering realization. To move beyond laboratory curiosities, we may need to abandon the idea of containment altogether and instead learn to create antimatter on demand as we need it from the energy of the ship itself. The ghost we are trying to cage is antihydrogen, a complete anti-atom. It is the simplest antimatter counterpart, a positron orbiting an antiproton. For propulsion, this neutral form is incredibly appealing, as it could be mixed with normal hydrogen in a controlled reaction. But its neutrality is also its greatest defiance. A penning trap which relies on electric charge is useless here. You cannot push or pull a neutral atom with simple magnetic or electric fields. So how do you contain something that refuses to interact? The answer lies in exploiting a far more subtle quantum property, its magnetic moment, using a device of astonishing complexity called an Ioffe-Pritchard trap. Think of an antihydrogen atom as a tiny, invisible compass. In the presence of a magnetic field, this compass wants to align itself. The Ioffe-Pritchard trap creates a magnetic field that is weakest at the very center of the device and grows stronger in every direction outward. It is like being at the very bottom of a magnetic valley. If our antihydrogen atom tries to move away from the center, it feels the field strengthening, which forces its internal compass to flip. That flip costs energy the atom does not have if it is sufficiently cold. So the atom becomes trapped, not by walls or charge, but by the very geometry of space itself, confined to the low point of an invisible energy landscape. This is the pinnacle of quantum control, a cage built from pure thought and precision engineering. The teams at CERN Alpha Collaboration, who first achieved this feat, describe a process of breathtaking delicacy. They must first produce and slow antiprotons and positrons separately, combine them to form antihydrogen, and then cool these anti-atoms to within a fraction of a degree above absolute zero. Only when they are this cold, this still, do they have a chance of being caught in the magnetic valley. The entire apparatus, a labyrinth of supercooled coils, lasers, and vacuum chambers, fills a large room. And for their monumental effort, what is the reward? They can currently trap a cloud of antihydrogen for less than an hour, at densities so low that the total mass is still immeasurably small. The apparatus is vast, but the amount of fuel it holds is virtually nothing. This starkly illustrates the next monumental gap. The trap is a magnificent scientific instrument, but an impossible engine component. We must ask, can a room-sized quantum experiment, requiring constant power and perfect stillness, ever be scaled down and hardened to survive the violent launch of a rocket and the harsh environment of space? The magnetic fields must be maintained without fail. The vacuum must remain perfect. The cooling systems must operate flawlessly for years. A single fault does not mean a leak, it means a catastrophic release. This forces a profound shift in perspective. Perhaps the container itself is the wrong thing to focus on. Maybe the future lies not in building a better bottle, but in reimagining the very materials that bottle would be made from, searching for substances that could, against all known physics, simply shrug off the touch of annihilation. Perhaps the greatest illusion in antimatter propulsion is the idea of perfect containment. Even if we could suspend the fuel itself in a flawless magnetic cage, the engine would still face a bombardment of pure energy from which there is no shield. Annihilation does not produce a gentle flame, it unleashes a storm of gamma rays and high-energy particles. These are not stopped by magnetic fields, they pass right through them, slamming into the physical structure of the engine itself. The chamber containing this reaction would face an energy flux greater than the interior of a star, so we must ask a seemingly impossible question: what do you build the walls out of? The search for an answer takes us to the extreme frontier of material science, where engineers confront the brutal effects of radiation damage. Nuclear engineers working on fusion reactors face a similar, though less intense, version of this problem. They describe three relentless foes. The first is embrittlement. When high-energy particles smash into a metal's crystalline structure, they knock atoms out of place, creating microscopic voids and dislocations. Over time, the material becomes brittle like glass that has been subtly cracked, losing its strength and flexibility until it could shatter under stress. The second is intense heating. Gamma rays deposit their energy directly as heat, requiring cooling systems of phenomenal capacity just to prevent the engine walls from melting into vapor. The third is induced radioactivity. The bombardment can actually transform the stable atoms of the wall material into unstable, radioactive isotopes. The engine itself would become a significant radiation hazard, glowing with its own dangerous light long after the reaction has stopped. So what materials could possibly survive? Conventional metals like steel or titanium would fail almost instantly. The focus turns to advanced ceramics, materials like silicon carbide or tungsten carbide, which have extremely high melting points and better resistance to radiation-induced swelling. Others look to amorphous metals or metallic glasses, which lack a regular crystalline structure and might be more resistant to the dislocations caused by particle impacts. But these are incremental improvements against an absolute threat. The most speculative ideas venture into the realm of metamaterials, substances engineered at the atomic level to have properties not found in nature. Could we design a material with a nanostructure that channels radiation harmlessly away, like a prism bending light? Or perhaps a layered composite that sacrificially ablates, constantly shedding its damaged surface while being replenished from within? These are concepts, not blueprints. Another radical approach seeks to avoid physical contact with the Fury altogether. This is the concept of the magnetic nozzle. Instead of allowing the hot plasma from the annihilation to push against a physical rocket bell, immense magnetic fields would be shaped to contain and direct that plasma, forming an invisible exhaust channel. The thrust is generated by the interaction of the plasma with this magnetic field, never touching a solid surface. It is an elegant solution in theory, but in practice it requires generating and controlling magnetic fields of staggering strength and precise geometry, fields powerful enough to contain a sun-like plasma within a machine. The material nightmare thus doubles. You must not only find a substance that can withstand indirect radiation bombardment, you must also engineer the systems that generate these containment fields to survive in the same hellish environment. It paints a picture of the engine chamber as the most hostile environment ever consciously designed, a place where matter is unmade and the very tools we build to harness that power are constantly being unmade alongside it. This forces a humbling realization. The challenge is not merely one of energy, but of longevity. Could any material system maintain its integrity long enough for a mission to another star, or would the engine simply consume itself from the inside out? The answer may lie not in stronger walls, but in a complete reimagining of the reaction itself, moving from a sustained burn to a series of controlled, microscopic explosions. That magnetic valley, a triumph of quantum engineering, comes with a constant and voracious appetite for electricity. This leads us to the fourth and perhaps most paradoxical challenge, the energy budget. It is a problem of simple, brutal arithmetic. How much power does it take to keep the most powerful fuel in the universe from touching anything? The answer, with today's technology, makes the entire venture seem absurd. Think of it as a bank account where the monthly fees to protect your money are larger than the balance itself. For antimatter to be a practical fuel, the energy needed to contain it must be a tiny, almost negligible fraction of the energy it will eventually release. This is the concept of break-even, a line we are currently nowhere near crossing. Analyses from aerospace research groups paint a stark picture. Current laboratory-scale penning and eye-off traps, designed to hold mere micrograms or even just atoms of antimatter, require continuous power inputs on the scale of megawatts. That is the output of a small power plant running non-stop just to keep a speck of fuel suspended. Where does all that energy go? The drains are relentless. First, the superconducting magnets must be chilled to near absolute zero, a process that demands massive cryogenic systems gulping liquid helium. Second, maintaining an ultra-high vacuum against even the faintest leaks requires powerful pumps running continuously. Third, the control systems themselves, the computers and sensors monitoring the trap's stability, add their own constant draw. This creates a devastating catch-22 for a spacecraft designer. You might need to install a dedicated nuclear fission reactor on your ship, not for propulsion, but simply to power the systems that prevent your antimatter fuel from annihilating prematurely. The mass of that reactor, its shielding, and its cooling systems could completely negate the mass savings that made antimatter attractive in the first place. It is the engineering equivalent of planning a hiking trip across a continent and deciding to carry a 2-ton bank vault on your back because you have a single, perfect diamond in your pocket. The diamond is priceless, but the cost of carrying its protection makes the journey impossible. So is there a path forward? Can we reduce this parasitic load? Researchers look to two frontiers. The first is the steady improvement in superconducting technology. New materials that become superconducting at higher temperatures could drastically reduce the cooling burden. The second is the environment of space itself. In the perpetual free fall and extreme cold of deep space, far from Earth's gravity and warmth, some of the containment tasks might become slightly easier. But these are marginal gains against a fundamental imbalance. The energy budget forces a humbling realization. We cannot just scale up our laboratory traps. We must reinvent them from first principles, designing containment architectures that are inherently low power. Perhaps this means moving away from continuous magnetic bottles and toward dynamic systems that only apply power in precise pulses. Or maybe it means integrating the fuel storage so intimately with the engine that the waste heat from one system helps power the other. Solving the energy budget is not about finding a better plug. It is about reimagining the entire relationship between the cage and its captive, searching for a way to make the universe itself help us hold the lightning. This labyrinth of magnetic fields is not a static cage, but a living architecture of force. To move beyond holding a few cold atoms, we must learn to contain a raging storm, a dense plasma of antimatter. For this, we look to our most ambitious attempts to bottle the sun, to the world of fusion energy. Here, physicists have spent decades designing intricate magnetic prisons to hold superheated hydrogen plasma, and their hard-won insights offer a blueprint for antimatter's next leap. The simplest upgrade from a basic trap is the magnetic mirror. Imagine a magnetic field shaped like a long tube that pinches tighter at both ends. Charged particles spiraling along the field lines will reflect back when they reach these stronger regions, like a marble rolling into a narrowing funnel and bouncing back. It seems elegant, but it has a fatal flaw. Particles moving just right can escape through the ends, a slow but constant leak that would drain our precious fuel over time. To solve this, we must bend the field into a circle, creating a continuous loop with no ends. This is the toroidal geometry of a tokamak, the iconic donut-shaped fusion device. Within its coiled magnets, plasma can race around forever, in theory. But nature abhors a perfect circle. In practice, the plasma develops instabilities, kinks, and wobbles that cause it to drift outward and touch the walls. The solution, born from decades of fusion research, is to twist the magnetic field as it goes around, braiding it into a stable helix. This combined configuration, where the field strength has a true minimum at the very center of the plasma, is called a minimum B geometry. It is the holy grail of magnetic confinement, a topological landscape where every direction away from the center is uphill. For an antimatter plasma, this could be the difference between a storage tank and a sieve. The engineering to create such a field is a symphony of precision. It requires arrays of cryogenically cooled, high-temperature superconducting coils arranged in complex, non-intuitive shapes. Some coils might be shaped like giant pretzels, others like helical springs wound around a central core. Together, they generate a contorted force field that the antimatter particles simply cannot navigate out of. Picture the core of an antimatter-powered ship not as a simple tank, but as a cavernous chamber housing this sculpted magnetic sculpture, glowing with a faint blue Cherenkov light from trapped particles, resembling a vast and silent art installation. Yet for all its beauty, the control challenge is immense. These fields must be dynamically adjusted in real time, using sensors and algorithms to anticipate and cancel out the slightest ripple of instability. The system must be self-healing, capable of compensating for a coil fault or a minor impact. This raises a pivotal question for deep space travel. Can we maintain this exquisite magnetic ballet, this dance of invisible forces, with absolute precision not for days, but for years or decades across the gulf between stars? Any failure is not a graceful shutdown, but a sudden, total conversion. This relentless demand for perfect control hints at a radically different path, one that abandons the idea of herding charged particles altogether and instead tries to hold them still with walls of pure voltage. Static electricity offers a different kind of cage, one built not from magnetism but from pure voltage. If magnetic traps are like sculpting invisible hills and valleys, electrostatic traps are about constructing perfect, repelling walls of force. Picture a single, positively charged antiproton. You can hold it still by surrounding it with electrodes carrying a strong negative charge. The particle is repelled from all sides, pinned in the center of an invisible box made of electric repulsion. This is the principle behind devices like the Kingdon trap, a beautifully simple concept where a charged particle orbits a thin, charged wire held in a stable loop by the balance of electric forces. For certain applications, this can be far simpler and require less constant power than a massive superconducting magnet, but there is a profound catch. This elegant cage only works if the prisoner is already nearly motionless. An antiproton with even a modest amount of thermal energy, a little jiggle of heat, will have enough speed to simply crash through those electrostatic walls. So before it can be stored this way, it must be cooled to within a whisper of absolute zero, a process that itself demands immense energy and complexity. The trade-off is clear: simplicity of containment in exchange for extreme difficulty of preparation. A more dynamic solution is the Paul trap, named for the physicist who invented it. This device uses oscillating electric fields to create a stable point in space. Imagine trying to balance a marble on the top of an upturned bowl. It constantly wants to roll off. But if you could vibrate the bowl at just the right frequency, you could create a dynamic equilibrium where the marble stays perched at the center. A Paul trap does this with electric fields, using rapidly switching voltages on its electrodes to create an effective restoring force that pushes a charged particle back toward the trap's center, no matter which way it tries to drift. This ingenious method is the workhorse behind modern mass spectrometers and atomic clocks, proving its reliability. For antimatter, it presents an intriguing possibility, a potentially compact and tunable containment system. Yet the challenge of scaling remains. Holding a few particles for measurement is one thing, holding the vast numbers needed for propulsion is another. The oscillating fields must be perfectly uniform, and the vacuum must be even more impeccable, as any stray particle could disrupt the delicate balancing act. In practice, the most successful laboratory traps are not purely magnetic or purely electric, but sophisticated hybrids. The penning trap, which we discussed earlier, is the prime example, combining a static magnetic field to control lateral motion with electrostatic fields to cap the ends. This hybrid approach gives researchers more control, allowing them to cool and manipulate antiprotons with laser-like precision. It represents the current pinnacle of our containment art, but as we have seen, it comes with a heavy infrastructure cost. Looking forward, engineers envision a layered system. A future spacecraft's antimatter fuel pod might not be a single device, but a nested series of specialized traps. Positrons, being lighter, might be held in a dense cloud within a high-capacity Paul trap. Antiprotons, with their greater mass, might reside in a robust penning-malmberg configuration. And if neutral antihydrogen is the goal, a final stage Eye-of-Pritchard trap would sit at the heart of it all. Each layer would act as a failsafe for the others, a defensive perimeter designed to prevent a single point of failure from dooming the entire mission. This layered defense raises a critical question. Could such redundancy ever be enough to guarantee safety? The very nature of antimatter means that any containment system is engaged in a perpetual, high-stakes struggle against entropy. Every pump, every coil, every voltage regulator is a soldier in a war against contact, and in space, there are no backup troops. A single micrometeoroid puncture, a solar flare-induced power surge, or the gradual degradation of a superconducting coil over decades could collapse the entire delicate architecture. The system would need to be not just redundant, but intelligent, capable of sensing an impending breach and reacting in microseconds to shunt or vent the fuel in a controlled manner, a task of almost unimaginable complexity. Safety, therefore, is not a feature you add to an antimatter engine. It is the central, all-consuming problem that must be solved before a single gram of fuel is ever loaded. It forces us to confront the ultimate question of risk, asking what level of inherent danger a society is willing to accept in the name of a journey to the stars. The ultimate safety protocol for an antimatter engine is not a set of instructions, it is a single, absolute commandment. There must be zero failures. This is not hyperbole, it is the cold, hard physics of the fuel itself. In a chemical rocket or even a nuclear reactor, a failure might mean a leak, a fire, or a meltdown, terrible events with a chain of cause and effect. For antimatter, a failure has only one outcome, immediate and total annihilation of whatever amount of fuel escapes its cage. The engineering philosophy shifts from damage control to the prevention of any breach, ever. Risk assessment specialists who study such systems describe a paradigm with no historical precedent, where the consequence of a single component fault is not just mission loss, but the potential for a catastrophic energy release. This transforms every engineering decision. You are not just building a machine, you are designing a perfect, perpetual state of stability against a universe that inherently favors chaos. The potential failure modes read like a catalog of cosmic paranoia. A micrometeoroid, smaller than a grain of sand but traveling at tens of kilometers per second, could puncture a vacuum chamber or sever a superconducting cable. A solar flare could induce a power surge strong enough to momentarily distort a critical magnetic field. Over decades of a deep space mission, material fatigue from constant radiation bombardment could weaken a structural support. Even a single high-energy cosmic ray could strike a trapped antiproton, giving it just enough energy to vault over its magnetic or electrostatic barrier and touch the wall. Each scenario, however unlikely, demands a defense. The safety architecture would therefore be a fortress of redundancy. Passive magnetic shielding, layers of superconductor coils, would encase the core storage modules, designed to maintain containment even if the primary system faltered. Power would come from multiple, independent sources, likely fission reactors with their own separate shielding, capable of taking over in microseconds. An active debris detection system, a kind of celestial radar, would constantly scan ahead of the spacecraft, ready to fire small thrusters to maneuver the entire vessel away from a detected dust particle. The scale of caution extends back to Earth. Ground-based testing of a full-scale antimatter containment system would not happen in a university lab. It would require a remote, heavily fortified facility, perhaps built into a mountainside or deep underground, operated by robots and monitored from kilometers away. The protocols would resemble those for handling the most dangerous biological agents, but scaled for a threat that operates at the speed of light. This brings us to a profound societal question, one of risk acceptance. Would any regulatory body on Earth, or any insurance company in existence, ever approve the launch of a vehicle carrying a significant quantity of antimatter into orbit over the planet? The political and public relations challenge may be as daunting as the physics. It forces a difficult but necessary conclusion. The very place we choose to build and store this technology becomes its first and most critical containment vessel. The journey may need to begin far from home, with the fuel manufactured and the ship assembled in the sterile void of space, where a failure, however tragic for the crew, does not risk the biosphere of our world. This shifts the dream from a terrestrial endeavor to a truly extraterrestrial one, a technology born not in our atmosphere, but in the cradle of the void it is meant to conquer. The fortress of safety must have an address, a location where this perpetual struggle against contact is waged. Do you keep the dragon in your basement, with all your tools close at hand, or isolated on a remote mountain where its fury cannot harm your home? This is the strategic dilemma of location, a debate that divides aerospace engineers and redefines the very meaning of infrastructure. On one side are the pragmatists who argue that antimatter must be born and caged on Earth. Our planet offers unparalleled technical support, massive power grids, advanced manufacturing, and the ability for human experts to intervene directly. Building the first generation of containment traps here seems the only logical step. Yet this logic collides with an undeniable risk calculus. Launching even a gram of this material from Earth's surface would be an act of profound global responsibility. A containment failure during ascent, however unlikely, would not be a local accident. It would be an atmospheric event. The political and public will to accept such a risk, however small the probability, may simply never materialize. This leads to the opposing vision, the concept of the orbital antimatter depot. Imagine a facility constructed in the high vacuum of space, perhaps in a stable orbit far from Earth, like a Lagrange point. Its primary advantage is the environment itself. The perfect vacuum we struggle to maintain on Earth is free and abundant. The deep cold of space passively aids cryogenic systems. And most critically, a failure at such a depot, while tragic for any crew and a devastating loss of resources, poses no direct threat to Earth's biosphere. The risk is contained to space itself, but this solution exchanges one set of nightmares for another. Constructing such a depot would be the most ambitious engineering project in human history. Every component, every superconducting coil, every precision machined part would have to be launched from Earth at tremendous cost, or manufactured in space from raw materials we have yet to learn how to process. Power would need to come from vast solar arrays or compact fission reactors, both requiring their own launch and assembly. Maintenance would fall entirely to robotics or spacewalking crews operating in bulky suits, trying to repair systems of hair trigger sensitivity. An illustrative future might see this infrastructure not just in orbit, but sourced from beyond Earth entirely. One speculative scenario involves manufacturing antimatter on the Moon. Its lower gravity would make launching the fuel to an orbital depot far cheaper, and a facility on the far side could be shielded from Earth's radio noise and public view. An even more distant vision points to the asteroid belt, where raw materials for shielding and construction are abundant, and the operational isolation is absolute. This progression reveals a deeper, almost philosophical hurdle. Does the dream of antimatter propulsion require that we first become a truly spacefaring civilization? The logistical puzzle suggests that the technology cannot be the key that opens the door to the stars, but rather the lock that can only be opened once we are already standing on the other side. It forces us to see the engine not as a singular invention, but as the pinnacle of an entire economic and industrial ecosystem in space. The cost of building that ecosystem may be the true price of the stars, a price measured not in dollars, but in generations of sustained effort beyond our atmosphere. This economic reality brings us to the final, most human dimension of the challenge, the staggering investment of time, treasure, and will require to even attempt such a leap. The price of a single gram of antimatter is not measured in dollars, but in the collective effort of entire civilizations. To even approach the development of a functional propulsion system, we must first construct a new branch of human industry, one that exists only to create and control the most elusive substance in the universe. The economic scale is almost incomprehensible, a cost-benefit analysis where the benefit lies a century or more in the future. Economists who study such monumental undertakings call this the waiting time, the vast desert of investment that must be crossed before any tangible return is seen. It is a period where money, intellect, and political will are consumed with no promise of a payoff within the lifetimes of those who authorize the first check. We have seen this pattern before, but never at this magnitude. The Apollo program at its peak consumed nearly 4.5% of the United States federal budget. The International Space Station represents over $150 billion of international cooperation across decades. An antimatter development program would make these endeavors look like modest pilot projects. The first phase alone would require not one, but a network of next-generation particle accelerators, each far more efficient than today's machines, dedicated solely to fuel production. Their construction could easily run into the hundreds of billions, and their energy demands would necessitate dedicated power plants, perhaps fusion reactors we have not yet perfected. Following that, the engineering phase would need orbital testing platforms, heavily shielded facilities in space where containment systems could be trialed in microgravity, away from Earth's biosphere. The bill for just this infrastructure could rival the gross domestic product of a mid-sized nation. Finally, the construction of a prototype vehicle, a vessel whose every component from its magnetic nozzles to its quantum computer controls represents a custom-made marvel of engineering, would demand another financial summit. So who could possibly fund such a voyage into fiscal oblivion? The likely answer is no single entity, but a consortium. A coalition of governments, perhaps through a newly formed interstellar agency modeled on early European sea exploration companies. Or a partnership between such an agency and a cotter of the most visionary and patient private entities, those willing to invest in a legacy that will bear their name long after they are gone. The United States Defense Advanced Research Projects Agency once explored this very idea through its 100-year Starship study, which framed interstellar travel not as an engineering sprint, but as a multi-generational societal endeavor requiring advances in medicine, ecology, and social systems as much as in physics. This perspective forces a difficult but essential question. In a world facing immediate challenges, from environmental shifts to resource pressures, can we justify diverting such staggering wealth toward a dream whose fulfillment our grandchildren may not live to see? The justification may not lie in the destination, but in the journey itself. The sheer difficulty of the task would catalyze breakthroughs across 100 fields, from energy production to material science, spin-off technologies that could transform life on Earth long before the first starship ever leaves the dock. The engine, therefore, is not merely a means of travel, but a forcing function for human evolution. The pure dream of antimatter propulsion confronts a brutal economic reality. But what if the solution is not to surrender the dream, but to dilute it? Imagine needing not a whole gram of this impossibly expensive fuel, but merely a speck, a single milligram. This is the promise of a hybrid architecture, a middle path known as the antimatter catalyzed fusion drive. Its principle is elegantly pragmatic. Use a match to light a bonfire. In this engine, the match is a tiny stream of antiprotons, and the bonfire is a conventional fusion fuel like deuterium and helium-3. The concept turns the problem on its head. Instead of using antimatter as the sole fuel, we use it as the ultimate spark plug. Here is how it would work. A microscopic pellet of fusion fuel is injected into a reaction chamber. At the same instant, a precisely timed pulse of antiprotons is fired into the center of that pellet. The antiprotons annihilate with protons in the fuel, creating an intense, localized burst of heat and pressure, a microscopic star being born in a flash. This sudden energy injection is so violent and concentrated that it can trigger nuclear fusion in the surrounding fuel, causing it to ignite and burn. The beauty of this approach is that the energy output from the fusion reaction is millions of times greater than the energy input from the antimatter annihilation. You get a tremendous amplification. Studies from NASA Advanced Concepts Office, like those in the former Project Orion lineage and more recent NASA Innovative Advanced Concepts proposals, have sketched out what this could mean. Such an engine would not have the almost magical specific impulse of a pure antimatter beam core rocket, but its performance would still be staggering. Estimates suggest specific impulses in the range of 10,000 to 100,000 seconds, compared to about 450 seconds for a chemical rocket. This translates to thrust levels high enough for practical travel within our solar system on human-friendly timescales. A mission to Mars could take weeks, not months. A voyage to the outer planets could be measured in months, not years. The engine layout for such a system begins to look more familiar, more like a next-generation fusion reactor. It would consist of an antimatter injector, a delicate particle beam system analogous to those in laboratory traps. The reaction chamber would be a robust sphere, likely lined with liquid lithium to absorb the neutron radiation from the deuterium fusion and convert it into usable heat. That heat would then be used to energize a propellant like hydrogen, which is expelled through a magnetic nozzle to create thrust. The magnetic nozzle is critical, as it prevents the super-hot plasma from vaporizing a physical rocket bell. The advantages of this hybrid path are compelling. The antimatter requirement drops from an economically impossible gram to a perhaps manageable milligram. The radiation environment, while severe, is more comparable to that of a fusion power plant, a problem engineers are already actively working on, and many of the core technologies, from magnetic confinement to pellet injection, have decades of development behind them through inertial confinement fusion research. This approach feels within the extended grasp of our civilization. You could picture a spacecraft, a bulky but powerful workhorse, using this system to rapidly ferry cargo and cruise between Earth, Mars, and the asteroid belt, becoming the backbone of a true interplanetary economy. Yet, this pragmatic vision forces a reflective question. Does using antimatter merely as a catalyst dilute the purity of the original dream? Is settling for a milligram a compromise that acknowledges our limits, or is it the only sane stepping stone that could ever lead us to the gram and beyond? Perhaps the dream was never about purity, but about progress. This hybrid engine would be the ultimate teacher, a practical school where we learn to handle antimatter in a relatively forgiving system, building the knowledge and confidence for more ambitious leaps. It represents a bridge between the possible and the fantastical. But for those who find even this compromise too cautious, there exists another path, one that embraces annihilation with a terrifying and beautiful directness. The hybrid engine is a bridge to the stars, but the true destination is a machine of terrifying simplicity. This is the pure antimatter rocket, a concept where the reaction itself is the exhaust, and the dream of a perfect engine with no moving parts becomes almost real. Here, fuel and oxidizer are the same thing, matter and its perfect opposite, meeting in a silent dance of light. It represents the theoretical endpoint of propulsion physics, a system of such efficiency it could unlock the galaxy. To understand its promise, we must look at two very different designs. The first is the solid core engine, a more conservative step from the hybrid model. In this design, antimatter annihilates within a heavy, shielded chamber, and the intense heat is used to warm a conventional propellant like liquid hydrogen. The hot gas then expands out a nozzle, just like in a chemical rocket, but with vastly more energy. It is powerful, but still limited by the melting point of its physical components. The second design is where the dream becomes pure. This is the beamed core engine, championed by visionaries like physicist Robert Forward. In this machine, there is no separate propellant, no physical nozzle to contain a plasma. Instead, the annihilation products themselves become the exhaust. When protons and antiprotons meet, they do not just produce gamma rays, they create a spray of charged particles called pions. These pions, moving at over 99% the speed of light, are the key. The engine uses immensely powerful magnetic fields, shaped into a nozzle of pure force, to capture and direct this spray of relativistic particles out the back. Think of it as a magnetic funnel catching lightning and bending its path to push the ship forward. The performance is almost mythical. While a chemical rocket might have a specific impulse of 450 seconds and a fusion engine tens of thousands, a beamed core antimatter engine could reach into the millions. This is not just an improvement, it is a transition to a different realm of physics. With such a system, a starship could accelerate at a comfortable 1 gravity for years, its crew living in Earth-like conditions while the ship steadily climbs to a significant fraction of light speed. The journey to Alpha Centauri shifts from a multi-generational odyssey to a voyage measurable in a human lifetime. Yet this perfect engine is built on a foundation of staggering difficulty. The magnetic fields required to steer pions are beyond anything we can generate today, needing strengths that would crumple any known material. And the pions themselves are unstable, decaying into gamma rays and neutrinos in mere nanoseconds. The magnetic nozzle must guide them out of the ship before that decay happens, a race against time measured in billionths of a second. This introduces the most brutal challenge of all, one that may be a true showstopper for human crews. How do you protect living beings from a continuous nuclear detonation happening just meters away? The annihilation chamber is a fountain of the most penetrating radiation known, a constant flash of gamma rays that no physical shield can stop without being impossibly heavy. For an unmanned probe, this is a solvable engineering problem of distance and shielding mass. But for a manned vessel, the radiation problem casts a long shadow over the dream. It forces a difficult but necessary question. Could the ultimate engine for reaching the stars be one that only our machines can ever ride? That perfect engine creates a perfect storm of radiation. Sitting next to an antimatter drive would be like living inside a particle accelerator, bathed in a constant, invisible sleet of gamma rays and high-energy particles. This is the sixth and perhaps most fundamental challenge for any crewed mission, the problem of shielding. The paradox is cruel. The very engine that could shorten a journey to another star also produces an environment that would be instantly fatal to any living thing aboard. Radiation biologists who plan for deep space missions work with a unit called the sievert, which measures the biological damage of radiation exposure. On Earth, we are protected by our atmosphere and magnetic field, receiving about 2.4 millisieverts per year. A career astronaut on the International Space Station might accumulate around 100 millisieverts over a 6-month stay, increasing their lifetime cancer risk. The flash from a solar storm can deliver a dose of several hundred millisieverts in hours, a serious emergency. Now, consider the environment near an annihilation chamber. Estimates suggest a crew member just a few tens of meters from the reaction, even with some basic shielding, could receive a lethal dose in seconds, not years. The traditional solution is mass, putting thick walls of dense material like lead, polyethylene, or water between the crew and the radiation source. But here, the math breaks the dream. To reduce the flux of deadly gamma rays to a safe level over a multi-year mission, you might need a shield of water or lead dozens of meters thick. One conceptual study calculated that for a certain beamed core engine design, the required shield mass could exceed 100,000 tons, more than the rest of the spacecraft combined. This completely negates the high-performance advantage of antimatter, turning the Starship into a sluggish, shielded fortress that can barely move. So we must ask, if we cannot block the radiation with sheer weight, can we bend it, deflect it, or trick it? Engineers look to two classes of solutions, passive and active. A clever passive approach is to use the ship's own consumables as shielding, positioning the water tanks, the food stores, and even the fuel for secondary systems around the crew habitat creates a protective buffer without dedicated mass. This is efficient, but it is rarely enough for the extreme flux of an antimatter drive. The water would need to be many meters deep, and once consumed on the journey, the protection would vanish. More promising are active shields, which use force fields instead of mass, for charged particles which make up a significant portion of the annihilation spray. This is theoretically possible. The concept is to generate a powerful magnetic field, shaped like a bubble around the crew module, that deflects incoming protons and electrons just as Earth's magnetosphere does. The challenges, however, are immense. The field would need to be incredibly strong and stable, requiring massive superconducting coils and immense power, creating the same parasitic load problem as the containment systems. And crucially, it would do nothing against neutral gamma rays which pass through magnetic fields unimpeded. To stop those, some highly speculative ideas have been proposed. One is the plasma window, the notion of creating a dense, magnetically confined cloud of plasma that could scatter gamma rays. Another, far beyond our current grasp, involves using artificial gravity or gravitational lensing effects to bend the radiation away, a concept that lives in the realm of hypothetical physics. The grim calculus from spacecraft designers often leads to a sobering conclusion. For a high-performance antimatter drive operating at full power, there may be no physically possible shield that is both effective and lightweight enough to allow for meaningful acceleration. This forces a pivotal and reflective question about the nature of exploration itself. If the engine that can take us to the stars is inherently incompatible with human biology, does that mean the dream of crewed interstellar travel is an illusion? Perhaps the answer is not to surrender the dream, but to reimagine the dreamer. The most practical path forward may accept that the first vessels to ride the light of annihilation will be robotic. A silent, resilient scout could be our first messenger to the stars. Freed from the overwhelming burden of protecting a human crew, an unmanned probe transforms the antimatter equation. It can carry a mere speck of fuel, endure radiation levels that would be instantly lethal, and embrace engineering risks no human-rated vessel ever could. This is the pragmatic path forward, where the dream of interstellar travel begins not with a majestic starship, but with a hardy, minimalist machine. Organizations like the Tau Zero Foundation, dedicated to making interstellar flight a reality, often point to this robotic pioneer as the logical first step. Imagine a probe perhaps no larger than a grand piano, its mass dominated not by living quarters, but by a rugged antimatter containment cell, a powerful laser communication array, and a suite of hardened scientific instruments. Its mission, propelled by just micrograms of antimatter fuel, would be to reach another star within a human lifetime. The concept builds upon ideas like Breakthrough Starshot, which envisions using powerful Earth-based lasers to push tiny light sails to relativistic speeds. But an antimatter-powered probe offers a crucial advantage: autonomy. It carries its own engine. This means it can perform critical mid-course corrections to precisely aim for its target, and most importantly, it could carry a second, smaller antimatter supply to fire in reverse, slowing down enough to enter orbit around a distant exoplanet. That ability to stop and observe is the difference between a fleeting glimpse and a detailed survey. The design philosophy for such a machine is brutalist simplicity. Every gram is sacred. There is no redundancy for comfort, only for absolute mission-critical functions. Its brain is not a general-purpose computer, but a set of deeply specialized, radiation-hardened processors running autonomous navigation and fault management software. Its communication system would likely be a focused laser, beaming a trickle of precious data back across the light years, a whisper carrying the secrets of another world. The advantages are profound. The fuel requirement drops from grams to micrograms, making production remotely plausible within this century. The safety overhead vanishes, as a catastrophic containment failure in interstellar space endangers no one. This allows engineers to use more aggressive magnetic nozzle designs and higher energy reactions, pushing the propulsion physics to its absolute limits. One can envision not a single probe, but a fleet, a coordinated launch of these robotic pioneers, each targeted at a different promising star system like Proxima Centauri or Tau Ceti. They become our eyes and ears, a distributed sensor network for humanity, sending back the first direct images of an exoplanet's surface, analyzing the chemistry of its atmosphere, and listening for the faintest whispers of activity. This raises a pivotal question: what scientific return could possibly justify the immense cost of building and launching such a machine? The answer may not be in a single discovery, but in the ultimate goal itself. The data payload justifying the mission is the achievement of reaching another world, confirming the presence of liquid water, mapping continents and oceans on a planet light years away, or even detecting the complex chemistry suggestive of a biosphere. Any of these would irrevocably change our place in the cosmos. The probe itself, a tiny speck of human ingenuity enduring a decades-long journey, becomes the most powerful statement we can make, that we are a species that looks outward and sends its curiosity ahead of itself. Yet, even this stripped-down vision confronts a final, deeply human challenge. If we succeed in sending a machine but can never follow ourselves, does the journey lose its meaning? A voyage to Alpha Centauri could become a single career. For most of human history, the very idea of reaching another star was a story of patience measured in millennia, a journey entrusted to generations unborn. The archetype is the generation ship, a self-contained world sailing through the void for 100,000 years. Its original crew long forgotten, their descendants living and dying within metal walls, their only purpose the faint hope of arrival at a destination their ancestors chose. It is a profound and haunting vision of dedication. Antimatter propulsion shatters that timescale. by enabling sustained acceleration to a significant fraction of light speed, perhaps 10, 20, or even 50%, the equation of interstellar travel transforms. A mission profile emerges that fits within a human lifetime. Consider a spacecraft accelerating at a comfortable 1/10 of a gravity for years, pushing its crew against a gentle, familiar force. After a decade of steady thrust, it would be moving at a blistering pace. Then it would coast for another decade or two, before beginning a matching period of deceleration to arrive at its destination. The total journey time to our nearest stellar neighbor shifts from an epic spanning civilizations to an expedition lasting perhaps 50 to 100 years. This is no longer a legacy, it is a commitment. An individual could leave Earth as a young researcher and arrive at Alpha Centauri in their advanced years, their life's work the journey itself. The contrast is staggering. A chemical rocket attempting the same trip might take 100,000 years, a span in which entire languages, cultures, and species could rise and fall. The antimatter-driven mission compresses that epic into a single human story. This compression is more than a technical achievement. It is an evolutionary step for our species. Visionaries like Carl Sagan often spoke of humanity's need to become a multi-world species as a way of preserving the light of consciousness. Interstellar travel is the logical, ultimate extension of that idea. It represents a transition from a solar species bound to our single star to an interstellar one, capable of spreading across the galactic neighborhood. This ambition forces difficult questions of purpose and governance. Who controls such a transformative technology? Is it the domain of a single nation, a global consortium, or perhaps an entirely new entity born in space? And what message do we send when we launch such a vessel? Is it a simple scientific probe, or is it an ark carrying the essence of our biology, culture, and knowledge? The answers define not just the mission, but the character of the civilization that builds it. The philosophical weight is immense. To master the containment of pure annihilation is to demonstrate a level of technological maturity and responsibility that may be a necessary rite of passage. It suggests a civilization that has learned to harness the most destructive force in nature, not for war, but for creation, not for ending worlds, but for reaching new ones. It is a test of our collective wisdom. Passing that test, however, requires more than grand visions. It demands tangible, incremental progress built in laboratories today, not in the shipyards of tomorrow. Deep within a concrete tunnel on the French-Swiss border, a few hundred specks of antimatter are being watched with more care than the crown jewels. This is the control room for CERN Antiproton Decelerator complex, where the theoretical challenges of containment become a daily, painstaking reality. Here, teams from experiments with names like Alpha, Asakusa, and Base are not building engines, they are learning to speak the language of antimatter itself. Their work is a masterclass in incremental triumph, proving that the dream is not static, but actively being pulled, particle by particle, into the realm of the possible. The Antiproton Decelerator is the starting point, a unique machine that does the opposite of what most accelerators do. Instead of speeding particles up, it takes the frantic, high-energy antiprotons produced in collisions and gently slows them down, cooling them until they are slow enough to be caught. It is a cosmic fishing net designed to catch the most elusive fish in the universe. Each experiment downstream then takes these cooled antiparticles and asks a different, fundamental question. The Alpha collaboration focuses on building and trapping complete antihydrogen atoms. Their apparatus is a layered masterpiece of superconducting magnets and ultra-high vacuum chambers, a cryogenic labyrinth where positrons and antiprotons are combined. Their signature achievement is holding clouds of antihydrogen for increasingly long periods, recently exceeding 17 minutes. Dr. Jeffrey Hangst, the spokesperson for Alpha, describes the goal with quiet intensity. We are performing spectroscopy on antimatter, he explains, shining lasers on these trapped anti-atoms to measure the light they absorb. Why? To see if antihydrogen absorbs light at exactly the same frequency as regular hydrogen. If it does, it confirms a cornerstone of physics known as CPT symmetry, the idea that the laws of nature are unchanged if you swap particles for antiparticles, reverse left and right, and run time backwards. A deviation, however tiny, would shake physics to its core and could hint at why our universe is made of matter at all. Meanwhile, the base experiment takes a different, equally precise approach. They work with bare antiprotons, measuring their fundamental properties with mind-bending accuracy. They have measured the antiproton's magnetic moment, a kind of internal compass strength, to a precision of 1 part in a billion, finding it to be a perfect mirror image of the protons. They have also performed the most precise test ever of the antiproton's charge to mass ratio. The apparatus for this is a sophisticated penning trap, chilled to just 4 degrees above absolute zero, where a single antiproton can be stored for over a year. The lead scientist, Dr. Stefan Ulmer, compares it to listening for a whisper in a hurricane. Every vibration, every fluctuation in the Earth's magnetic field is noise we must eliminate to hear the true signal of the antiproton. These are not propulsion experiments, but they are laying the essential groundwork. Every time they improve their vacuum, achieving pressures lower than that found on the moon, they are advancing the technology needed for a stable fuel bottle. Every time they develop a more stable power supply or a more sensitive detection method, they are solving a piece of the engineering puzzle. One of the most significant recent breakthroughs came from an international team who managed to laser cool antiprotons. Imagine trying to slow down a speeding bullet by shining a flashlight on it. Laser cooling uses the gentle pressure of photons to rob particles of their thermal energy, making them colder and slower. Applying this technique to antiprotons, a feat long thought nearly impossible, is a game-changer. Colder particles are easier to trap in denser clouds, a critical step toward the quantities needed for any practical application. The moment the data confirmed successful cooling was not marked by shouts in the control room, but by a silent, profound relief. A barrier had fallen. So how does measuring a magnetic moment or holding a few hundred anti-atoms for minutes relate to a star drive? The connection is through the language of control. These experiments are teaching us how to manipulate antimatter with the same finesse we use to handle atoms of ordinary matter. They are proving that we can measure it, cool it, trap it, and observe it without it instantly disappearing. This growing mastery directly informs the theoretical design studies for propulsion. The data on how antiprotons behave in complex magnetic fields feeds into simulations for magnetic nozzles. The techniques for stacking and storing particles suggest ways to scale up containment. Each decimal point of precision in measurement shrinks the margin of error for a future engine designer. This painstaking foundational work transforms antimatter from a mythical substance into a laboratory material, one whose rules we are slowly, definitively learning to write. These laboratory triumphs feed directly into the digital drafting tables of conceptual design. Within the archives of NASA's Innovative Advanced Concepts program and the private research groups that follow its lead lie blueprints for vessels that have never been cast in metal, yet are bound by the strict laws of physics. These are not flights of fancy, but rigorous engineering analyses, mathematical thought experiments that ask one profound question: if we had the antimatter, how would we actually use it? One of the most detailed pathways is the antimatter catalyzed microfission fusion concept. It is a hybrid of staggering complexity, designed to extract the maximum possible thrust from a minimal amount of antimatter. The engine cycle reads like a symphony of nuclear processes. First, a microscopic pellet of fissionable material, like americium, is injected into a reaction chamber. A pulse of antiprotons is fired into its heart, triggering a fission explosion. This explosion then compresses and ignites a shell of fusion fuel, like deuterium and tritium, surrounding the core. The result is a two-stage nuclear detonation, all sparked by a vanishingly small amount of antimatter. Studies led by researchers like Dr. Stephen Howe, who has explored these ideas for decades, calculate that such a system could achieve specific impulses around 10,000 seconds, with thrust levels high enough for rapid travel to the outer planets. The engine itself would be a pulsating beast, firing these micro-explosions several times per second, its thrust controlled by the precise timing of pellet and antiproton injection. Another, more exotic design aims for the stars directly. The vacuum-to-antimatter rocket Interstellar Explorer System, or VERIS, is a concept that seems to cheat the production problem entirely. Proposed by physicist Friedworth Winterberg, it turns the vacuum of space itself into fuel. The idea uses an immensely powerful space-based laser to create particle pairs, matter and antimatter, directly from the quantum foam of empty space. These particles would then be separated by magnetic fields, with the antimatter channeled into a storage trap and the normal matter discarded. It is a concept that lives at the very edge of known physics, requiring laser intensities we cannot approach and efficiencies we can only dream of, but it illustrates the lengths to which theorists will go to solve the fuel supply dilemma. To understand the practical gulf between a concept and a craft, we can look at a detailed NASA study for an antimatter-powered orbiter to the moons of Jupiter. The spacecraft in these computer models is dominated not by a sleek engine, but by a massive cylindrical shield protecting the sensitive science payload from the relentless gamma-ray bath. The propulsion module is a dense cluster of superconducting coils, cryogenic tanks, and a reaction chamber the size of a small car. Mission simulations show a journey time measured in months rather than years, a revolutionary leap. Yet buried in the technical appendices are the assumed breakthroughs: a stable antiproton production rate 1,000,000 times current capability, a magnetic confinement system with 99.9999% efficiency, and materials that can withstand years of pion bombardment. The principal investigators of these studies are the first to acknowledge the chasm between the blueprint and the builder's yard. Dr. Robert Frisbee, who led early antimatter propulsion studies at NASA Jet Propulsion Laboratory, often framed the work as identifying the showstoppers. "We are not saying we can build this tomorrow," he would note. "We are mapping the canyons we must eventually cross." The designs reveal a fundamental split in philosophy. Some, like the Catalyzed fusion drive, prioritize high thrust for practical solar system exploration, accepting lower efficiency for the sake of power. Others, like certain beamed core concepts, aim for the extreme specific impulse needed for interstellar travel, accepting minuscule thrust that builds over years. This divergence asks a reflective question: do these intricate studies represent a viable roadmap, or are they primarily exercises in optimistic extrapolation, useful for guiding research but not yet construction? Their value is undeniable, for they translate the abstract challenges of containment and radiation into concrete engineering parameters, giving today's laboratory researchers a distant star to steer by. Their optimism, however, is always tempered by the quiet host of secondary challenges listed in the final pages of each report, the ones without clear solutions, waiting for the next generation of minds to even begin the work. That silent beacon of infrared light reveals a seventh, relentless adversary. An antimatter engine is so phenomenally efficient at creating energy that its greatest threat may be its own success. The problem is not a lack of power, but an overwhelming, inescapable surplus of heat. Even with a perfect magnetic nozzle and flawless containment, a brutal fraction of the annihilation energy will be deposited as heat directly into the engine's structure and shielding. In the airless void of space, this heat has only one path to escape: radiating away as infrared light. This makes thermal management not a secondary system, but a primary design constraint that could dictate the entire shape of the spacecraft. Thermal engineers who design deep space probes speak of heat rejection with a kind of sober reverence. On Earth, excess heat can be dumped into the air or water through conduction and convection. In space, those avenues vanish. Every watt of waste heat, from the power-hungry superconducting magnets to the gamma rays soaking into the reactor walls, must be shed through radiation. The physics is unforgiving. The rate at which a surface radiates heat depends on its temperature to the fourth power. To reject a massive amount of heat without melting the radiators themselves, you need an enormous surface area, often requiring panels that dwarf the rest of the vessel. The calculations are staggering. Consider a beamed core engine producing terawatts of thrust power. Even if 99.9% of that energy is channeled perfectly into the exhaust, the remaining 0.1% absorbed by the structure is still a gigawatt of heat, enough to power a large city. To radiate that away while keeping the radiator panels at a manageable, say, 600-degree temperature, you would need a radiating area equivalent to several football fields. These are not delicate fins, they are vast, fragile landscapes of metal, likely constructed from lightweight alloys like titanium or beryllium, etched with channels for liquid metal coolant. Their design implications are profound. Such colossal structures create immense drag during acceleration, not from air but from the inertia of their own mass. They become the single largest physical component of the ship, a sprawling, vulnerable target for micrometeoroids. A puncture in a coolant line could spell mission failure as surely as a magnetic bottle collapse. Picture the vessel from a distance, not as a sleek dart, but as a strange, radiant flower, its petals glowing a deep cherry red in the infrared, a brilliant beacon announcing its presence and its profound waste to the cosmos. This forces a pivotal question for systems engineers. Is all this waste heat truly just waste? Could it be captured and put to work? Some concepts suggest using thermoelectric materials to convert a portion of this thermal gradient directly into electricity, powering the ship's subsystems and reducing the load on the main reactors. Others imagine using the heat to vaporize a secondary propellant for low-thrust maneuvering. Yet these are partial solutions at best, recovering only a tiny fraction of the lost energy. The thermal burden is an inescapable tax, a thermodynamic tithe paid for wielding such concentrated power. It integrates into a maddening puzzle where solving the heat problem makes the ship larger and more vulnerable, while minimizing radiators risks cooking the very systems that keep the antimatter contained. This dance between power, mass, and thermal survival becomes the final, intricate layer of the engineering labyrinth, where every gain in propulsion efficiency must be weighed against the cost of disposing of the heat it inevitably creates. The final blueprint reveals a puzzle of impossible compromises. You have an antimatter core, a humming sphere of cryogenic coils and perfect vacuum, demanding absolute stillness. And you have a working starship, a roaring symphony of pumps, thrusters, and spinning gyroscopes, a creature of vibration and electromagnetic noise. Integrating them is not engineering. It is a high-stakes negotiation between two realities that fundamentally reject each other. This is the domain of the systems architect, whose job is to see the spacecraft not as a collection of parts, but as a single, fragile organism where a change to the heart alters the brain. The core dilemma is one of antagonistic optimization. Making the magnetic bottle more stable might require heavier supports, which then demands more thrust, which requires more fuel, which needs a bigger bottle, in a vicious cycle that can spiral out of control. Every decision ripples through the entire design. Place the antimatter store close to the engines to shorten fuel lines, and you bathe it in crippling radiation. Place it near the crew for easier monitoring, and a containment failure becomes an instant catastrophe. The likely layout of a notional ship becomes an exercise in defensive spacing. The antimatter core, a heavily shielded vault, sits amidships, suspended in a web of active vibration dampeners, perhaps even on its own independent inertial platform, floating within the ship like an egg in gelatin. It is connected to the main engines at the stern by heavily shielded transfer lines and draws power from reactors placed at a safe distance, likely in their own shielded pods. The crew habitat sits at the opposite end of the ship, behind every possible buffer of water tanks and supply stores, putting maximum mass between them and the gamma-ray fountain. The integration nightmares are legion. The powerful magnetic fields from the containment coils can wreak havoc on sensitive navigation instruments, requiring them to be placed far away or housed in their own metal cages. The constant, subtle hum of cryogenic pumps and vacuum systems creates a spectrum of micro-vibrations, frequencies so tiny you cannot feel them, but enough to jiggle a trapped antiproton out of its perfect equilibrium. And then there is the sheer mass penalty of the structure itself. The supports holding the antimatter core must be immensely strong to withstand launch forces, yet they must also be thermal insulators to prevent heat from leaking into the cryogenic systems. They become complex, multi-layered composites, each gram agonized over. We have seen a whisper of this challenge before, in projects of exquisite sensitivity like the James Webb Space Telescope. Its sunshield and mirrors had to deploy in orbit with nanometer precision, a ballet of mechanisms that could not be tested fully assembled on Earth. For an antimatter ship, the integration complexity is that of Webb, multiplied by 100, with the added imperative that it must work perfectly the first time, and then continue working without maintenance for decades. This raises a profound question of reliability. Can a system with millions of interdependent parts, where a single faulty sensor or a slowly degrading seal can lead to total loss, ever be trusted with a journey of 100 years? There are no service stations between stars, no possibility of a repair crew. The vessel must be not just redundant but resilient, capable of diagnosing its own ailments and reconfiguring itself around damage. It must endure not as a machine, but as a living testament to our foresight, carrying its own fragility across the light years. That humming vault of antimatter is a promise that must not break, not for a year, not for a century. Its flawless operation demands a new kind of engineering philosophy, one that plans for the slow, inevitable creep of time itself. This is the challenge of deep space endurance, where a mission measured in decades exposes components to stresses they were never designed to survive. We are familiar with machines that last, the Voyager probes still whispering back to us after nearly half a century. But their longevity comes from radical simplicity, from having almost no moving parts. An antimatter containment system is the opposite, a dense forest of complex, high-stress systems, each with its own hidden clock. Consider the superconducting magnets, the heart of the magnetic bottle. They are not just coils of wire, they are rivers of current flowing without resistance, frozen in a state of perfect conductivity. Yet over decades, even superconductors can experience a phenomenon called flux creep, where the magnetic field they generate slowly, imperceptibly, begins to diffuse through the material. It is like a dam developing a microscopic seepage, a gradual weakening that could, over a century, distort the perfect geometry of the trap enough to allow a catastrophic loss. Then there are the vacuum seals, the barriers that maintain a void emptier than space itself. They are under constant bombardment from stray radiation, a slow irradiation that can make polymers brittle and metals fatigue. A seal does not fail with a bang, but with a whisper, a molecule at a time, until a pristine vacuum begins to degrade, and within the trap itself, a more insidious accumulation occurs. Even in that perfect void, over decades, a few stray atoms from the chamber walls will inevitably find their way in, attracted by static charge. This atomic dust, a few particles per year, slowly contaminates the stored antimatter cloud, increasing the chance of a premature annihilation event. These are failure modes without precedent, problems that unfold on a timescale longer than the careers of the engineers who built the system. Specialists who design deep space probes speak of the difference between 50-year reliability and 500-year reliability. The first is an extreme challenge of material science. The second is an act of faith in predictive models we cannot fully test. How do you build for a journey longer than recorded history? The strategies become increasingly profound. Redundancy is no longer enough. You need redundancy with intelligence. Imagine critical components like a magnet power supply, not just duplicated, but triplicated or more, with the ability for the system to cold swap between them without a millisecond of interruption. The ship must be able to amputate a failing limb and grow a new one. This leads to the concept of self-repairing systems, where the vessel carries onboard fabrication units, perhaps 3D printers capable of using recycled material or raw asteroid feedstock to manufacture replacement parts. A cracked support bracket or a degraded radiation shield tile could, in theory, be identified, melted down, and reprinted by robotic arms, a form of metallic healing. But all these safeguards come at a cost: the relentless tax of mass. Conservative design margins balloon, requiring structures twice as thick, power systems with 10 times the needed capacity, just to ensure they still function at 99% after a century of decay. The ship becomes heavier, slower, and more complex with every layer of protection, a paradox where the quest for perfect reliability can make the mission itself impossible. This is where the role of artificial intelligence transforms from a tool into a partner. The AI pilot would not just fly the ship, it would listen to it, a digital physician constantly monitoring a million vital signs. It would run predictive maintenance algorithms, comparing the slow drift of a magnet's field against models of flux creep, forecasting a failure years before it happens and scheduling a proactive component swap. An illustrative scenario unfolds in the silent depths. A sensor deep within the antimatter core detects a faint, rhythmic fluctuation in a secondary containment field. The AI cross-references this with power grid loads, thermal readings, and vibration data. In milliseconds, it diagnoses not a failing coil, but a resonance induced by the slow spin of a distant coolant pump. With no human to consult, it makes a decision. It reroutes power from non-essential systems like a dormant science lab to bolster the fluctuating field, while simultaneously commanding the pump to alter its rotation speed by a minuscule fraction. The anomaly smooths out. A potential cascade has been averted by a silent symphony of autonomous correction, millions of miles from any help. This capability raises a pivotal and unsettling question. Is absolute reliability a myth when dealing with the raw forces of annihilation over cosmic timescales? Can any system, no matter how redundant or intelligent, guarantee a 0% chance of catastrophic failure across a century? The ethical dimension of this calculation cannot be ignored. If we launch a vessel carrying such power, we are implicitly accepting some probability, however infinitesimal, of a tragic outcome. This acceptance is the final, sobering weight on the shoulders of those who would build such a ship, a burden of responsibility that extends across generations and into the stellar dark. Mastering annihilation forces a question that transcends engineering. We are not merely solving a technical puzzle, we are deciding what kind of civilization we wish to become. The power to convert mass into pure energy is, by its nature, dual use. The same magnetic bottle designed to propel a starship could, in a different configuration, become the heart of a weapon of unimaginable scale. A single gram of antimatter represents an energy release comparable to a nuclear detonation, but without the need for a critical mass or complex fission trigger. This introduces a profound ethical burden, one that philosophers of technology have long warned about. The moment we learn to store significant quantities, we create a new class of existential risk. The precautionary principle suggests we should halt development until we are certain of the consequences. Yet the opposing view, the exploratory imperative, argues that to turn away from such knowledge is to deny our nature and our future. This tension defines our relationship with cosmic fire. The debate centers on a balance of perils. On one side lies the risk of creating a new, ultimate explosive, a tool that could make conventional warfare obsolete by its very presence, escalating global tensions to an unprecedented degree. The environmental impact of large-scale production on Earth also presents a serious concern, as the energy demands and potential for catastrophic accident, however remote, could reshape how communities view such facilities. An accident during testing or storage would not be a local event, but a global moment of reckoning. Ethicists point out that we have navigated similar forks before, with nuclear fission and biotechnology, but the sheer energy density of antimatter places it in a category of its own. The knowledge itself becomes a permanent part of our technological repertoire, and with it, the universe becomes a slightly more dangerous place. Yet, on the other side of the scale rests what scholars term an existential opportunity. The very power that could threaten our world might be the only thing that can ultimately save it. By unlocking the stars, we do not just gain new destinations, we gain a future free from a single point of failure. A catastrophic asteroid impact, a global pandemic, or any planet-wide disaster would cease to be an end to human history if our species were thriving on multiple worlds. Antimatter propulsion could be the key that transforms humanity from a single planet species into an interstellar one, ensuring the long-term survival of consciousness itself. This is not merely exploration for its own sake. It is an act of cosmic stewardship, a backup plan for the human experiment. Navigating this divide demands more than brilliant engineers. It requires wise governance. Who should control such a transformative technology? It is unlikely to remain the sole province of any single nation or corporation for long. The parallel is often drawn to the international regimes that grew around nuclear technology, like the Non-Proliferation Treaty. But antimatter would necessitate a framework far more robust and universally adhered to, a new kind of interstellar accord drafted before the first gram is ever produced. It would need to address production quotas, storage security, testing protocols, and the absolute prohibition of weaponization, with verification mechanisms of unprecedented transparency. The goal would be to treat antimatter not as a weapon or a commodity, but as a common heritage of humanity, like the deep seabed or outer space itself, to be used only for peaceful exploration and the benefit of all. This global conversation is the final, and perhaps most difficult, containment vessel we must build. It is a structure made not of magnetic fields, but of laws, norms, and shared vision. It asks us to look at the child with the keys to the universe's arsenal and decide collectively what lessons we must teach before the first door is opened. The journey to the stars was never just about physics. It is a test of our maturity. Can we develop the wisdom to match our ambition, to hold a power that destroys matter itself and use it solely for creation? The answer will determine not just if we reach the stars, but who we are when we get there. That conductor must never miss a single note. Managing an antimatter engine is a control problem of impossible complexity, a task so fast and so precise it can only be entrusted to an artificial intelligence of a kind we have not yet built. Every microsecond, billions of data points stream in, magnetic field strengths in the trap, thermal readings from the nozzle, particle densities in the exhaust plume, and the subtle vibrational hum of the ship's superstructure. A human operator could not even perceive this torrent of information, let alone react to it. The AI must act as the ship's central nervous system, making constant microscopic adjustments to keep the entire system in a state of perfect dynamic balance. Control theory specialists describe this as maintaining a system in a metastable equilibrium, like balancing a needle on its point while standing on a moving train. The smallest deviation left uncorrected can amplify into a catastrophic instability. Machine learning engineers working on such concepts envision algorithms that do not merely react but predict. By modeling the engine's behavior down to the quantum level, the AI could run millions of simulations in parallel, forecasting potential failure modes hours or days before they manifest, and taking preemptive action to steer the system away from danger. This is not just automation, it is technological precognition. The architecture of such a mind would likely be hierarchical, a layered intelligence. At the lowest level, dedicated, hardened processors would manage the immediate physics, the 1,000 adjustments per second needed to keep an antiproton cloud centered in its magnetic bottle. These would be specialized instruments, single-minded in their purpose. Above them, a higher-level mission AI would synthesize this raw data into a coherent picture of engine health, managing power distribution, thermal loads, and navigation. This overseer would possess the ability to learn and adapt, its algorithms evolving over the decades-long mission to understand the unique quirks and slow degradations of its own vessel. It would become an expert on this one specific machine, in a way its human creators never could be. The requirements for this intelligence are non-negotiable. Its programming must be inherently fail-safe, designed so that any loss of signal or processing error defaults to the most conservative possible action, reinforcing containment fields and initiating a safe shutdown sequence. It must contain ethical behavior locks, absolute prohibitions hardwired into its core decision, pathways that prevent it from ever interpreting a command or a situation in a way that would jeopardize the crew or a populated area. And critically, its hardware must be resistant to the very environment it operates in, shielded against cosmic ray-induced bit flips, those random high-energy particles that can flip a 0 to a 1 in a computer's memory and corrupt its logic. Consider an illustrative scenario midway through a voyage. A micrometeoroid, too small for the debris radar to track, punches a pencil eraser-sized hole through a secondary coolant line near the magnetic nozzle. Pressure drops, temperature sensors in the engine bell spike within milliseconds. The low-level thermal control AI registers the anomaly and reroutes coolant, but the damage is done. The heating is distorting the magnetic field geometry. The mission AI, monitoring the field stability data, detects a growing asymmetry. In less time than it takes for a human to blink, it cross-references this with the thermal data, the ship's orientation, and the stress models of the nozzle structure. It predicts a cascade, a field collapse leading to plasma contact and a massive heat surge in 11.2 seconds. It does not alert the crew, there is no time. Instead, it executes a pre-programmed emergency protocol. It commands the antimatter injector to cease firing, ramps up the secondary containment fields to maximum strength to secure the stored fuel, and initiates a controlled venting of the now uncontained plasma in the engine chamber through auxiliary ports. The ship shudders, alarms finally sound for the human crew, but the catastrophic engine failure has been averted. The AI has performed a graceful degradation, sacrificing thrust to preserve the core of the ship. This capability forces a profound and unsettling question upon us. Can we ever truly trust a non-human intelligence with control over such destructive potential? This is not a question of capability, but of philosophy and psychology. The trust cannot be granted, it must be earned through a long, visible chain of technological maturation. We would need to see such systems operate flawlessly for years in automated interplanetary freighters, then in unmanned interstellar probes, building a legacy of reliability before a single human life is entrusted to its care. The final guardian of the antimatter, therefore, may not be a physical wall or a magnetic field, but the proven, predictable wisdom of a mind we built to be better than our own. The century-long journey to the stars will not begin with a roar of engines, but with the quiet hum of a laboratory magnet. This is the essential truth of any grand technological leap. It is built not in a single bound, but on a scaffold of patient, incremental steps. To transform antimatter from a laboratory curiosity into a reliable star drive requires a deliberate, multi-generational roadmap, a staircase of ambition where each step validates the next. The first stage, already unfolding in facilities like CERN, is about deepening our fundamental mastery. Over the next 20 years, the focus must be on enhanced laboratory confinement and precision measurement. The goal is not grams, but control. Researchers will push to hold larger clouds of antihydrogen for not just minutes, but days or weeks. They will refine laser cooling techniques to achieve ever colder, denser antiproton plasmas. Every decimal point of precision in measuring an antiproton's magnetic moment, every new method for efficiently producing and slowing these particles, is a brick in the foundation. This phase is about learning the complete alphabet of antimatter's behavior, so we can later write the instruction manual for an engine. The second stage, perhaps 20 to 50 years from now, moves from basic science to applied engineering. This is the demonstration of sustained containment of useful quantities in a dedicated, ground-based testbed. Useful here is relative, perhaps micrograms instead of nanograms, but it represents a million-fold increase over today's capabilities. This stage demands the convergence of several critical technologies. It will require next-generation particle accelerators, far more efficient than today's, designed specifically for antimatter production rather than pure research. It will depend on advances in materials, likely the arrival of practical high-temperature superconductors that drastically reduce the crushing energy burden of magnetic traps. The testbed itself would be a remote, heavily fortified facility, a proving ground where engineers can integrate containment, power, and cooling systems into a single, stable architecture. Success is measured not by thrust, but by duration and stability, proving we can hold a meaningful amount of fuel safely for months or years on Earth. Only after proving we can cage the dragon on the ground do we attempt it in its natural habitat. Stage 3, spanning perhaps 50 to 80 years, is the development of a space-based test facility. The advantages of the orbital environment are compelling. The perfect vacuum and deep cold of space are free, and a containment failure poses no risk to Earth's biosphere. This facility would be humanity's first antimatter depot, a robotic outpost constructed at a Lagrange point or in high Earth orbit. Its primary mission is to master containment in microgravity, where the subtle effects of convection and sedimentation vanish, and to begin testing engine components like magnetic nozzles and particle injectors in a relevant environment. The power for this depot would likely come from compact fusion reactors, another technology that must mature in parallel. This stage is about building the off-world industrial base, learning to assemble and maintain these exquisitely sensitive systems using robotics and autonomous operations, a critical skill for any future interstellar vessel. The final prelude to the stars is Stage 4, the integrated system test on an unmanned solar system probe. 80 to 100 years from now, all the accumulated knowledge condenses into a single vehicle. This probe, perhaps a scaled-down version of a future starship, would carry a functional antimatter propulsion system, likely a hybrid catalytic design for its more forgiving engineering. Its mission is not to leave the solar system, but to conquer it, demonstrating rapid transit to the outer planets. A successful flight to Neptune and back within a few years would validate the entire technological stack, from production and storage to engine operation and thermal management, in the harsh reality of space. This probe is the final exam, and passing it grants the license to build for the interstellar void. This roadmap is not a prediction, but a plausible pathway, and its timeline is profoundly optimistic. It assumes sustained, monumental funding and unbroken political will across generations, a continuity of purpose that humanity has rarely demonstrated outside of wartime. Technology historians note that comparable leaps, like the development of nuclear power from laboratory physics to commercial reactors, took roughly 40 years and consumed the focused resources of superpowers. Our roadmap is more than twice as long and infinitely more complex. It depends on a cascade of secondary breakthroughs in artificial intelligence for autonomous ship management, in advanced composites for radiator panels, and in closed-loop life support for any future crew. Each stage is a gatekeeper, and failure at any point stalls the entire endeavor for decades. This forces a reflective question upon us, one that is less about physics and more about spirit. Are we, as a civilization, capable of planting an acorn, knowing that only our great-grandchildren will rest in the shade of the oak? Our ability to sustain a vision across centuries, to invest in a future we will never see, may be the ultimate test and the true signature of a species ready to graduate from its cradle. The dream of annihilation sits at the farthest edge of a vast and varied landscape. To understand its true place, we must zoom out and survey the entire field of advanced propulsion, a constellation of competing ideas, each promising to unlock the solar system and beyond. Antimatter is not the only candidate for fast space travel, and a clear-eyed comparison reveals where its terrifying power is truly indispensable. The competitors are formidable, each with its own passionate advocates and decades of research. On one side are the fusion drives, like the legendary Project Daedalus study from the 1970s. This unmanned interstellar probe design relied on inertial confinement fusion, using powerful electron beams to ignite pellets of deuterium and helium-3. Its theoretical performance was stunning, capable of reaching Barnard's star in about 50 years. Magnetic confinement fusion, the approach pursued for earthly power plants, offers another path, using tokamaks or stellarators to contain a sustained fusion plasma for thrust. Then there are the fission fragment rockets, which skip the heat exchange step of nuclear thermal propulsion entirely. Instead of using fission to heat a propellant, they direct the high-speed fragments from split atoms directly out a magnetic nozzle, achieving very high efficiency. And perhaps the most elegant of all is beamed energy propulsion, exemplified by concepts like breakthrough starshot. This removes the engine from the spacecraft altogether, using a gigantic ground-based laser array to push a wafer-thin light sail to a fraction of light speed. It is a beautiful solution for tiny robotic probes. To compare these concepts, we need a common language. Engineers use two primary metrics, thrust and specific impulse, which is a measure of fuel efficiency. Think of thrust as raw power, the ability to push a heavy ship quickly. Specific impulse is like miles per gallon, how far you can go on a tank of fuel. A chemical rocket has high thrust but terrible specific impulse, about 450 seconds. A fusion drive might have moderate thrust and excellent specific impulse in the tens of thousands of seconds. An antimatter beamed core engine offers mind-bending specific impulse in the millions of seconds, but its thrust, while steady, is comparatively low, requiring long acceleration times. A verbal comparison chart would place these systems on a spectrum. Chemical rockets are here today, proven but limited. Nuclear, thermal, and fission fragment rockets are within our near-term grasp, offering a several-fold improvement. Fusion drives represent a monumental leap, but one that awaits the solution of containment and ignition on a spacecraft scale. Beamed energy is brilliant for ultra-lightweight payloads but struggles to scale for crewed missions. And then, at the extreme end of both performance and difficulty, sits antimatter. At propulsion conferences, researchers often present this spectrum with a note of sober realism. Antimatter is the gold standard for energy density, but its technological readiness is essentially zero. Its unique selling proposition is brutally simple. It is the only known method, compliant with our current understanding of physics, that could realistically propel a manned vehicle to a meaningful fraction of light speed, enabling true relativistic travel within a human lifetime. Fusion is powerful, but its energy density is still thousands of times lower. This suggests a future not of one winner, but of a tailored toolkit. Imagine a solar system where different engines are used for different missions, much like we use trucks, ships, and airplanes on Earth. High-thrust, moderate-efficiency fusion drives might become the heavy-lift freighters, rapidly moving cargo and crews between Earth, Mars, and the main asteroid belt. For more delicate scientific missions to the distant ice giants, a fission fragment rocket's high efficiency might be perfect. And for the ultimate journeys to the enigmatic Oort cloud at the solar system's fringe or to another star, only the concentrated fury of antimatter would suffice. This layered future raises a pivotal and unsettling question. Could a sudden, unforeseen breakthrough in a competing technology, like room temperature superconductors for fusion or a novel laser material for beamed energy, make the antimatter dream obsolete before it is even born? It is a real possibility. The history of technology is littered with paths not taken, ideas superseded by simpler, cheaper alternatives. The uncertainty is not a flaw, but the very nature of pioneering research. We push on the hardest problem not because we are certain it is the only solution, but because in striving for the stars, we force every other technology to become better. The antimatter challenge, in all its terrifying complexity, serves as a forcing function for our entire civilization, a beacon in the extreme that illuminates the entire path forward. The cathedral was not built because the architects knew every stone would fit perfectly. It was built because the vision of reaching heaven demanded it. Our pursuit of antimatter propulsion is a cathedral of the mind, an edifice of collective ambition whose true value may lie not in the final spire, but in the strength we gain laying every stone. The drive to contain pure annihilation speaks to something fundamental in the human spirit, the same impulse that carved statues from mountains and sent whispers of data past the edge of our sun's influence. This endeavor, in its sheer impossibility, becomes a mirror. We see our limits and then we strive to move them. Thought leaders from across the centuries have echoed this sentiment. The late Stephen Hawking often spoke of looking up at the stars, not down at our feet, as the only way to understand our place in the universe. Elon Musk frames monumental challenges like Mars colonization as a way to ensure the future of consciousness itself, to make humanity a multi-planet species. These are not just engineering goals, they are narratives. They are stories we tell ourselves about who we are and what we might become. The antimatter rocket is the ultimate plot device in that story, a symbol of a civilization mature enough to wield the power of creation from destruction. But the plot is not just about the climax. The most profound impact of this century-long struggle will not be the engine itself, but the avalanche of innovation it forces into being along the way. These are the spin-off technologies, the quiet revolutions that will seep into every corner of our lives. To build a perfect magnetic bottle, we will need to reinvent superconductivity, likely discovering materials that lose all resistance at far more practical temperatures. That breakthrough alone could transform energy grids, transportation, and computing. The quest for an unbreakable vacuum will drive advances in materials science and pumping technology, with applications in semiconductor manufacturing and medicine. The robotics needed to assemble and maintain such a delicate system in space will push autonomy and precision to new levels, refining everything from surgical assistance to disaster response. And the artificial intelligence required to manage this symphony of forces will become a master of prediction and stability, a form of narrow intelligence with profound implications for managing complex systems like climate models or global logistics. This cascade of innovation has a powerful historical precedent. The Apollo program, born from geopolitical tension, did more than land people on the moon. It catalyzed advances in integrated circuits, materials science, and software engineering, seeding the digital revolution. It inspired a global generation to look toward science and engineering, filling classrooms with students who dreamed of being part of something larger than themselves. The cultural impact was immense, reflected in art, film, literature, and a pervasive sense of optimistic futurism. The antimatter challenge holds the same potential. It is a grand, unifying puzzle that can focus our intellectual and creative energies, offering a narrative of hope and capability in a world often preoccupied with more immediate concerns. It tells a story not of limitation but of latent potential, so we arrive at the final, reflective question. Even if we never hear the silent thrust of an antimatter engine, even if the perfect magnetic bottle remains a laboratory dream for another 500 years, is the journey of trying worth the cost? The answer may be found not in a ledger but in our spirit. To choose the hard path, to invest in a future we will never see, is the definitive act of a species that believes in its own tomorrow. It is a declaration that our curiosity is boundless, that our desire to explore and understand is a fundamental part of our identity. The value is in the striving itself, in the millions of small solutions to impossible problems, in the generations of engineers who will look at a star and not just see a point of light, but see a destination waiting for a key we are still learning to forge. The antimatter rocket, therefore, is more than a machine. It is a crucible. In our attempt to build it, we are not just testing physics, we are testing ourselves. We are asking if we have the patience, the wisdom, and the collective will to reach for a power that could destroy us and choose instead to use it only to create. That choice, that enduring act of hopeful ambition, may be the most important thing we ever build. Our journey through the impossible reveals a profound truth about human nature. We are drawn not to the easy path, but to the one that forces us to become more than we are. The saga of antimatter propulsion, from the raw equation of mass and energy to the silent, perfect cage of a magnetic trap, is a story of our species looking into the cosmic forge and deciding to learn its secrets. The obstacles are not just barriers, they are invitations. Each showstopper, whether it is the astronomical cost of production or the unforgiving physics of gamma-ray shielding, marks a frontier of human understanding. To solve them would mean we have learned to speak the language of the universe at its most fundamental level. The pursuit itself becomes the prize, transforming us from passengers on a planet into architects of our own interstellar future. This transformation is already underway in quiet laboratories and on digital drafting tables where the patient work of centuries is beginning. It is a testament to an ambition that thinks not in years but in generations. The vision of a silent ship riding a beam of pure light between stars is more than a destination, it is a mirror. It reflects back to us a civilization capable of extraordinary patience, cooperation, and foresight. It asks us to build not for our own glory, but for the legacy of those who will come long after us, to plant a forest whose shade we will never sit in. That act of planting is the ultimate expression of hope. It says we believe the future is worth the immense, difficult gift of our present effort. So the question shifts from if we can build such an engine to what we become in the trying. Every advance in superconducting materials, every new insight into quantum control, every simulation of a magnetic nozzle is a step not just toward the stars, but toward a more capable, more resilient version of ourselves. The mastery we seek over annihilation may ultimately be a mastery over our own limitations. The incredible thing waiting to be known, as Sagan suggested, might be our own potential. If this voyage to the edge of physics and imagination has sparked your curiosity, we invite you to join us for the next exploration. Subscribe to stay on the frontier and share your perspective below. Which of these monumental challenges do you believe will be the most difficult for our descendants to solve?